Hello, welcome back. Today's graph is of projectile motion on Earth, or rather, you can give it any gravity in meters a second, and it'll, to the best of its ability, calculate or rather show the projectile motion of a ball being thrown as it progresses. So, like, if I were to run this, it's slowed down, but this is like, for example, if I threw it at an angle of 30 degrees from the ground at 25 meters a second, this is roughly how far it would travel. About 55. It would go roughly about 55 meters. I can also change the initial height. So it can the endpoint will be more like 69 meters. I plan to add like changing the initial X position, although that isn't as important on my roster. But yeah, you can change it. If I set this back to 0, you can change the launch angle. So like you can throw it like 70 degrees, 80 degrees in the air. Won't go very far, but it'll go pretty high. Yeah, you can do that. You can change the initial velocity at which it is thrown. As you can see, smaller initial velocities mean it doesn't go very far. But like if I send it like 25 meters a second, that's gonna go pretty far. It's gonna go like 45 meters. I actually don't know how long that is because I'm an American, so yeah. It's also a good way to visualize why no matter no matter what you're basically for any initial velocity of a projectile with any gravity, you're not going to get better results for distance than 45 degrees just because of the way it works. And keep in mind, this is with initial height 0. If initial height was, say, not greater than 0, then that'd be a whole different story, but it is not. So yeah, that's that. Technically, you can change the gravity. I don't like that. It doesn't feel natural. In fact, actually, this graph is not made for it. This graph is not made for changing the gravity calculations, although I might just have to change a few things. I might just have to change a few things. I'll fix that in the snapshot. Yeah, the main components of it are getting the x and getting like, so this triangle here, this triangle is representative of the initial velocity vectors of this ball. So like if I were to stop it running for just a second, I had to reset it. If this ball is, say, about to be thrown, or rather, it has barely even left my hand. It is barely even left my hand. It basically still has all of its initial velocity and launch angle. This is the x and y component of its initial velocity. This is the direction it would go along this straight line if there was no gravity, and this was the way it was thrown. But because there's gravity, it'll instead follow this parabolic path downwards because, well, that's how gravity works. I'd be kind of surprised if you didn't, unless you're, I don't know, someone on the ISS. So yeah, you can run it. Particularly the initial x and y components of the velocity are very important to the calculations. Yeah, if you because actually what's actually going on here, the position is not this this trajectory path is something that I've added afterwards. The motion of this ball right here is actually entirely given by two equations. And I'm just going to turn this off for just a sec. This parabola right here represents the height of the ball in meters as time goes on. Everything here is a function of time. This represents the height of the ball in meters as time goes on. And conversely, or not conversely, but respectively, this here represents the x position of the ball as time goes on. And if you look, as I change the initial velocity, these change. And I think they even change if I change the launch angle, they also change. Yeah. So that this calculates the height. If you weren't to look at this trajectory, technically the x variable here would be time, and these are modeling. This one models height, this one models this distance, but this graph is in meters. So what I've done, I've made the ball's coordinates depend on height or these two graphs. I've made the ball's coordinates depend on these two graphs as a function of time. And then afterwards, I have done some funky stuff, which I will not get into. Oh, yeah, that's why the change in gravity earlier didn't work, because I hard-coded some stuff. But basically, this will give a model of the trajectory this ball will take. Not only that, but also like the apex point, the point in its trajectory where it'll be at the maximum height. So here it's at about 27.5 meters, where it'll reach a maximum height of about 8 meters. Yeah, that's about it. It's not very sophisticated. I mean, you can go through it one by one to like see how its position changes. Yeah, not much to it. If I can, I'd eventually like to start modeling a physics engine, or maybe not a physics engine, but at least get some bouncing going, because I just love to see how that works. One of the things I'd love to do is make a stratified. What the heck is going on here? Oh, it's because I use trig. It just breaks. Yeah, basically what I'd love to have happen is like, if I were to drop a ball on some, I don't know, let's drop a ball on any graph or curve, I could use some trigonometry, or no, not trigonometry, I could use some calculus to get like the normal vector of where it collided and stuff, and do that to add like bouncing. I think that would be really cool. Although that would definitely take a lot of effort. Heck, I couldn't even figure out how to get bouncing working here, but one day. But yeah, that's today's graph. Projectile motion. Later. Thanks for coming.